Hello, once again, AP Calculus students. We are still talking about area here, section 4.2 of Larson's textbook. And we are kind of in the middle of talking about this process that we refer to as the limit process in finding an area, which is somewhat rigorous, but contains just some algebra that just can be slightly pesky at times, but it's usually something that students can handle pretty effortlessly. And the first thing that I would like to do is to go ahead and sketch a graph of this y equal 4 minus x squared. And because my x values that serve as my boundaries, 1 and 2, are relatively small, I can utilize as much as my x-axis there. And if I do let x be 0 for the purpose of sketching this graph, I would have a y value of 4. An x value of 1 would give me a y value of 3, I believe, and an x value of 2 would essentially lie on the x-axis. So the other partitions of my y-axis would look like that. And if I were to switch colors here to sketch this parabola or portion of this parabola, perhaps it would look a little something like this. And didn't do a good job of switching colors there very well. And then if I were to sketch in the left boundary x equal 1, I pretty much have my enclosed region. Now I'd have to finish it off by verifying that the right boundary would be indeed x equal 2, and the x-axis, which wouldn't necessarily have to be drawn in here, but that would serve as the lower boundary. And lo and behold, here in yellow I would have a region that I am asked to find the area of. An irregular shaped region that geometry doesn't help us very much with, but of course calculus will. And the limit process is one way to do that. Now, we have always been talking about partitioning our region into a certain type of shape, and rectangles seem to do the job quite nicely. Now, I don't mean for these two figures that I've drawn to serve as rectangles, because of course they aren't. And they won't be until I cap them off at the top somehow. And that sort of brings us to a crossroad in the whole, what do we do? Do we use the left endpoint or the right endpoint in order to define our rectangle? One way will cause a great headache with the algebra that lies ahead. The other way won't be nearly as bad, but yet they would both give you the same answer. So if that is the case, we would probably want to go with the choice that gives us a much less of a headache with the algebra, and that is the right endpoint for reasons that I'll explain in just a bit. So the right endpoint would mean that these rectangles are finished off by moving from the right side over. So essentially, I would have a rectangle that would look like this for rectangle number 1. And then rectangle number 2 sits right alongside him. Now, we basically have an infinite number of these rectangles. That's what the limit process is all about. And we were just going to find the area of each of these guys, and we will add them all together. So that takes you to the formula for the area of a rectangle, which of course is just area equaling the width times the length. And by definition, the width of any of these rectangular figures that we decide to place under our curve goes by b minus a over n. Basically, the right endpoint, in this case 2, subtract the left endpoint 1, divide by the number of rectangles that you have, where it's highly likely in some previous exercises that you've been working, it has been a specific finite number of rectangles. Perhaps it was 4, perhaps it was 5, 8. And you would plug that value in for n. But in this case, it's a little bit more arbitrary, so we call it 1 over n for our width. Now, it's the length that's a little bit tougher to deal with. The length will be a function in this case. It will utilize the equation here of the curve, and although it's not written in function notation, we could certainly address the y value as being sort of like an f of x. And in that case, then our length would be f of some value along the x-axis that we decide to plug in. Now, this particular example utilizes something that we don't tend to think about very often, and that's the fact that our left endpoint up here is not a 0. And that's got to be a sort of a red flag that you're going to have to think about any time that you have a left endpoint other than 0. Because by definition, the length is defined to be f of wherever you're starting as your left endpoint, added to that sort of a counter of the width, if you will, of the rectangle that you're doing. Now the width of the rectangle we know is 1 over n each time. Right? These are rectangles all of uniform width. But because we're taking so many of them into consideration, we would multiply that by I. That would serve as sort of our counter. Now in this particular case, we would see that our a is 1, and the 1 over n times I is just going to be I over n. So we have f of 1 plus I over n. So if we were to multiply these together, we basically have our area formula for our rectangles. Now, let's go ahead and do that. And as we write this out, we can go ahead and specifically evaluate f of 1 plus I over n. In fact, if it makes it a little easier, we could get a common denominator, n plus I over n. Sometimes I think that's a little easier to do. So I would have this function up here, 4 minus x, that's going to get replaced by the contents within the parentheses. So 4 minus the quantity n plus I all over n squared. Now let's keep in mind, yes, I have a width times the length. That's great. That's wonderful. But what's the deal with this I? Well, what kind of role does he play? Well, remember, as I said before, he is the counter. He is keeping track of what rectangle you're finding the area of, starting with the first rectangle all the way up to the nth rectangle. Once again, I ask, how many rectangles are we dealing with? Well, in a limit process problem, the answer to that is infinity. So we will place a limit statement and allow that n to become infinity. And once you've written this entire limit, summation, length, and width, you have your building blocks, your formula, if you will, for finding the area of this very obscure shape. Now, that's the good news. The bad news is yes, this is where the algebra will come into play. That will allow you to start simplifying this summation expression. So let's go ahead and do that. Let's go ahead and address what's happening with this n plus I over n squared. That's our first order of business. And we will go ahead and expand the n plus I in the numerator, which of course is n squared plus 2in or ni. It really makes very little difference right now. Plus I squared. Hopefully you can all follow that binomial expansion. And then the denominator, of course, would be n squared. Well, what could we do with this? Well, I think we could get a common denominator. That could make things even a little easier for us. So I'm going to write this off to the right. And that common denominator would be n squared, of course. 1 over n sits and waits patiently. While I have 4n squared over n squared, replacing my original 4. And then everything else just falls into place. Now that I have this common denominator, I'm going to go ahead and combine some like terms. Something that I tell my students in my classroom all the time is that a good calculus student, or just a good math student in general, will always write their work so that each step is equivalent to the step just prior and to the step afterwards. And that's what we've been doing here. And as we go ahead and combine our two fractions with the common denominator n squared, we got to keep in mind that we have to distribute this minus sign now. So as I combine 4n squared minus n squared, of course, is 3n squared, I need to send that minus sign right through. So slowly but surely, things are looking better. We do have a few more things that we need to take care of, and each step, I think we get a little bit closer to the solution. At this particular point, I think it's important to recognize what is a constant and what is a variable. And it's very key to look at this index, I, and realize that that really is the thing that's changing. The I is really what varies, so perhaps we can think of the I as the variable. Any other letter, although it might look like a variable, really isn't. It is a constant. And if you take a closer look, this 1 over n and this n squared here in the bottom are both going to be eligible to come out in front of the summation because they're not affected by this I. This I can change as much as it wants, and they're not going to change anything. They're just going to be 1 over n cubed. So let's do that. Now let's not get a little over anxious and try to bring out the 1 over n cubed in front of the limit because that's not going to happen. This limit does affect things that have n in them. So we're going to stop that 1 over n cubed factoring right out there before the summation, but not before the limit. Now that does clean up things just a little bit inside. We're just left with the expression 3n squared minus 2. I'm going to go ahead and swap the n for the I. It'll be kind of apparent why I do that in a moment. Minus I squared. Now, a very key part of the problem here, and it's one that's going to involve perhaps you researching or looking back in your notes. No doubt your teacher has talked to you about these. 3 different formulae that would be used in evaluating different types of summations. And the first one is the summation of a constant as I runs from 1 to n. Well, essentially this is just saying I'm taking a constant c and I'm going to add it to itself n times. That would give me a result of c times n. Pretty easy. And then another formula that deals with the summation as I goes from 1 to n of plain old I. Things like adding, situations like adding 1 plus 2 plus 3 plus 4 up to a certain level. And perhaps you were taught this in an Algebra 2 class, but n times n plus 1 over 2 would be the result of that particular formula. And yes, there is even a third, one that's not nearly as popular as the previous two, but it's going to be used here, and as you can probably guess, it is the summation formula for I squared. Now once again, I just seem to be throwing these out at you, and it might be important that you guys look at them, make sure that they did show up perhaps in your notes in the preliminary discussions with the section on area. But the summation for I squared is n times n plus 1 times 2n plus 1 over 6. You're going to find these are going to be used in this particular problem. So, what does that mean for us? Well, our limit statement still in the picture, and our 1 over n cubed is still hanging around. But what I'm going to do is decide to change the way that I write this summation expression and essentially write it as 3 separate. Now this is a step that many students decide to skip. I personally don't have any problem with that as long as you use the correct formula in the correct fashion. We're all okay. But this might make my next step a little bit clearer. And it's basically rewriting each of these summation expressions using the appropriate formula that we have over here to the right side of the screen. So the limit drops on down, the 1 over n cubed drops on down, and now we start getting to work. The summation of 3n squared. Well, 3n squared is sort of like a constant. This is like our c. So if we look at this formula here, it says take that c and multiply it by n. And that's exactly what we're going to do. We're going to take 3n squared and multiply it by n, which gives us 3n cubed. Take a look at the next summation expression. Now notice it has a 2n, which is, yeah, it's sort of like a constant. It's a constant that has nothing to do with this I, very similar to this 1 over n cubed that had nothing to do with I. And we can bring that 2 times n out in front of just this summation. We don't want to bring it all the way out in front. That would be bad. Just in front of that summation. And in that case, that 2n is just sitting and waiting on multiplying by the result of the summation of I, which happens to be this guy up here. So if you multiply this 2n by n, we now have 2n squared, and then just drop in the n plus 1 all over 2, and we are good to go. Yes, we could cancel those 2's, but I'm going to do something in a little bit that's actually going to change this denominator, so there's no point in doing that at this point. And the I squared summation, that's probably the easiest one to manipulate here. It's got the most complicated formula, but there's nothing more to it than just rewriting that. And if you take a look at what you've just accomplished, it's a pretty important step. Do you see any more summation expressions? Summation symbols? No, that's a great thing. And you want to keep in mind that when the summation formula is utilized, the summation expression is gone. It's done his job. Now there are some students that might be viewing this, and some students certainly that I have in class, that can actually look at this entire expression and they can see that the answer is 5/3. That's what the answer is going to be. It's 10 over 6, which would reduce to 5/3. But some students can't see that, and that's perfectly fine. And we're going to go ahead and take a moment and do some more algebra so that that answer of 5/3 is a little bit more obvious. And the algebra that I'm speaking of is nothing more than doing some distribution or some binomial multiplication. So if we do that, this 2n squared just will distribute through very easily. And I'm also going to, let's not deal with this minus right now. Let's take care of that later. So 2n squared times 1 would just be 2n squared. Denominator of 2. Now over here, this might be the more difficult algebra of the problem, but it's nothing more than a binomial times binomial FOIL, if you want to call it that, and distributing of the n. So if I take care of that, I would have 2n squared multiplied by an n, 2n cubed, of course. The outside inside would produce 3n multiplied by n would be 3n squared, and then 1 times 1, 1 multiplied by n would be n. Slowly but surely we're getting there. And then in one more step, to see what this limit result's going to be, I'm going to get a common denominator. And it's probably clear that this common denominator will be a 6, which means we would have to multiply the 3n cubed by a 6, giving us 18n cubed. Since I already have a denominator of 2 here, I'm going to multiply by 3 on the top and the bottom. And if it's okay with you, I'm going to distribute that negative sign as well. So it'll take a hold of this guy, changing it to negative. And as far as this last fraction is concerned, really the only thing that needs to be done is to distribute a negative sign. And we are so close to our result, or our final answer now. Now, at this particular stage, I think it's important that we take note that what I'm about to highlight in orange is really the only thing that matters in this problem at this stage. Those two guys matter, and of course this guy matters. And I would say the 6 in the denominator along with this n cubed matters. And let's not forget that what's driving this whole problem the rest of the way is that limit statement. Now what do I mean by that? Well, if you recall, when you find the limit as n approaches infinity, your job is just to really focus on what is the highest degreed exponent in both the numerator and the denominator. And you're going to find out that in order for these limit questions to have answers that are numeric, that actually show an area that's truly there that you can see, the degree of the top and the bottom will have to be the same every single time. If they're not, you've probably made some kind of an error. And it's clear that the degree here is 3. And if you just simplify 18n cubed minus 6n cubed minus 2n cubed, you would have 10n cubed. Divided by a 6n cubed is going to give you that 10 over 6, or 5/3 that we talked about. Now, if that's a little too much for you to handle, then by the time that you simplify this a little bit more completely, I think it becomes a little bit more clear what the answer is going to be. Remember, I have 10n cubed, and really the rest of that I'm writing is just not real important, because now I'm focused only on this value and this value. 10 divided by 6, or 5/3. And that is the actual area that lies under this curve. And we could probably verify that if I took a look here